In one of his books on path integrals, in particular quantum mechanics and path integrals, written by Feynman and Albert Hibbs, Feynman derives the Schrödinger equation from the path integral formulation. And here in this video I want to show you the method that Feynman used in his book, and I will use a slightly different notation, but we will follow Feynman's steps to derive the Schrödinger equation. So we start by assuming that we have a formula for the path integral. In particular, we consider a one-dimensional space. So a one-dimensional space means that we consider one dimension of space, the x-axis if you want, and we have one dimension of time. So we call that the time variable. So let's assume that we have one endpoint for the calculation of the path integral. We need one initial point and one end point. The endpoint will be y, and this will be a function x calculated at the final time that we call t1, and for the sake of convenience sometimes we might just label it as x sub 1. And then we have one starting point for the path integral that we call x, and this would be the function x, the position function evaluated at the initial time t0, or if you want we can call it x0. And the path integral evaluates all possible paths between these 2 points. So one of them, for example, might be the classical trajectory, and the classical trajectory gives rise to the Euler-Lagrange equations if you want. So that's classical physics, but in quantum mechanics you have different amplitudes associated to different trajectories, and you have to sum over all those possibilities to find the quantum analog of the classical trajectory. So you have an infinite amount of such trajectories. So for example, we might consider this point, which is x evaluated at some time, I don't know, t prime, and the path integral evaluates, so at this point we sum over all the possible paths, and we multiply that by the corresponding amplitude, and we obtain the overall, some overall average, let's say, in the path integral. So in mathematical terms, we might write the following. So the amplitude at the end point, which is a function of, so the amplitude is psi, we evaluate the amplitude at the end point, x1, t1, so at the coordinate related to space and the coordinate related to time. And this amplitude at the end point can be obtained by means of a path integral. In particular, we have to integrate, we have an infinite number of integrals actually, and these integrals are weighted by an exponential e to the I. Then we have the action divided by h bar, and the action is an integral itself of the Lagrangian, and we integrate from the initial time to the final time, so from t0 to t1. Here we have the Lagrangian, and we assume that we have one particle with mass m, and the position of the particle therefore would be x of t. That's what this x of t0 and this x of t1 represent. They are the position of particles. They represent positions of this particle, and we also have a potential, let's say v of x. So it's just a particle in a potential field. So the Lagrangian will be a function of x and of x dot, so the time derivative of the position, and we have to integrate over time, of course, this Lagrangian. And then inside the path integral we have amplitudes evaluated at the initial time, x0, t0, and we have to integrate over, so we have a measure related to x, to the position. So this dx here is proportional to a product of differentials of the kind dx of t0, so dx is proportional to dx of t0 dot 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 dx, and we approach the end point. So x1 would be dx of t1, but we get closer and closer without summing over the final point, so we assume that this differential, this measure here, is proportional to this product, and here we have t1 minus a small increment of time dt. So you can take this as an assumption if you want, and as I said, each point of a certain trajectory can be integrated in a certain direction to denote the fact that we don't have just one trajectory. We have an infinite amount of trajectories, and that's why we have this complicated measure. This complex integral here with this weight from t0 to t1 is some kind of propagator which propagates the wave function from the initial point to the end point. And when I say initial point, I mean the initial point in space and the initial point in time, if you want. So we reach this. And x0, t0, x1, t1, they might differ by finite amounts. So x1 minus x0 might be finite, and t1 minus t0 might be finite, but that's our choice. We can choose x1 and t1, and in order to find the Schrödinger equation, what we will assume now is that these differences are differentials, are small quantities. So x1 is close to x0 and t1 is close to t0. So we assume that t1 is equal to t0 plus a small increment that we might call dt, or if you want, we might just call it epsilon in the following. And x1 is equal to x0 plus a small increment that we might call dx, but we might also call it era. So I will use era in the following. Therefore, the path integral can be rewritten in the following fashion. In particular, this infinite product of differentials will become just one differential. It will be dx of t0 if you think about it, because x0, which is x of t0, is very close to x1, which is x of t1. So intuitively you can understand that this infinite product here will boil down to just one term, dx of t0, which is dx0, if you want. And by the way, let me also multiply the integral here by a constant, and we divide by a constant that I will call it a, and this is just a normalization factor, and we will see why it is convenient to rewrite it in this form. But if you want to go deeper into the theory, you have to study path integral. So we assume that we take this as a starting point. Then let's rewrite the path integral in this case when these conditions hold. So when the points are very close to each other, both in time and in space. So we have to integrate over all the possibilities from minus infinity to plus infinity. Then e to the I divided by h bar is multiplied by the Lagrangian evaluated at a point which is close to y. So remember that we have to evaluate the Lagrangian between the points x and y, so between x0 and x1, or if you want x of t0 and x of t1, but in this case they are very close to each other, so we might just choose a point inside the interval, and then we multiply the Lagrangian by the increment of time, which is just epsilon. So we can choose a point, for example, we can choose the initial point, which is x, and we can rewrite it as a function of the final point, because we can write it as y minus era. So y minus era, since x1 is equal to y and x0 is equal to x, if you want, you can see it from here, that x is equal to y minus era. So I hope that this notation will not confuse you. You have to think about it a little bit, but it's not complicated. And then we have to evaluate the derivative. Here we would have x dot. And the derivative x dot can be evaluated, for example, like this. We might take the final point minus the initial point, so y minus x, and we divide by the increment in time, which is just epsilon. But y minus x is just equal to era. So here we can simply write era divided by epsilon, and then we multiply the Lagrangian by the increment in time, which is epsilon. And then here we have psi of x0 t0. So let's call, we already know that x0 is equal to y minus era, so we can write it like this, and let's call t0 just t. So I'm just writing t here. We have to integrate, of course, over x0, but x0 is also equal to x. And remember that, so we keep the endpoint fixed, y, because it will be the point that we have also in the final result. Y will appear here, so we have to think that y is fixed, and therefore dx is also equal to minus d era, if you want. So you take the differential of this expression and you get dx equal to minus d era. Simple as that. So we really have to integrate over eta in this expression. Remember that we have also divided by the constant a, which is just a constant, and this would be equal to psi of the endpoint, which is y, and also the endpoint in time. And we can rewrite the endpoint in time as t, the initial time, plus the small increment epsilon. So this is the starting point where we have to write the Lagrangian for one particle in a potential field, and then we have to use some Taylor expansions to rewrite the expression, and lo and behold, that will coincide with the Schrödinger equation. So this was actually the most difficult part so far, to set up the problem and also the notation. But after we do that, we are actually ready to use our autopilot, because that's really just a bunch of calculations that are not so difficult from here. So the Lagrangian for a particle in a potential field is quite easy to write. So we have the kinetic term, which is the mass times the velocity squared divided by 2, and the velocity squared we already know can be written as era divided by epsilon. So we have era squared divided by epsilon squared, and then we have to subtract the potential field, which is v of x. But remember that now we are not using the variable x, we are using the variable y. So if you want to rewrite x in terms of y, we have to write y minus era, like this. Now let's rewrite the expression 1 over a integral from minus infinity to plus infinity. Then we can rewrite the exponential like this: e to the I m era squared divided by 2 h bar epsilon. And then we also have another exponential which contains the potential field. So we have minus I over h bar v of y minus era times epsilon. Now, since both epsilon and era are small, they are infinitesimal quantities, we will keep all the quantities up to first order. So if we want to keep only the quantities up to first order, we make a negligible error if we replace v of y minus era times epsilon by v of y times epsilon. So we are making a negligible order if you think about it, because if you expand the function v of y minus era, you will also get a term proportional to era. But when we multiply that by epsilon, we will get something proportional to era by epsilon, and therefore this is a higher order term that we can just neglect. Then we have, of course, psi of y minus era t, which is the same as before, and then remember that instead of writing dx, we can write minus d era. And then this is equal to psi of y t plus epsilon. Now we are ready to Taylor expand this exponential here. Then we expand also psi of y minus era, because eta is small and also epsilon is small, remember that. And we can also expand the right hand side here, psi of y of t plus epsilon as well, because epsilon is small. So if we do that, what we get is something of the following kind: 1 over a integral from minus infinity to plus infinity e to the I m eta squared divided by 2 h bar epsilon. And let me also tell you that this epsilon here in the denominator comes from this. So here we would have had something like this: epsilon squared multiplied by epsilon. But of course, epsilon divided by epsilon squared just gives us epsilon. So that's why I have this expression in the first exponential. Then when we expand this to first order, we have 1 minus I over h bar v of y times epsilon. And then when we expand this psi, we get this. So in this case, I will expand this expansion to second order, and let me tell you why. The fact is that you can see that we have an integral over eta, right? And eta is small, but when we expand this, we have, so let's do that. So for example, we have psi of yt, when we set eta equal to 0, then we have a second term of the kind minus eta, and then we have the derivative of psi with respect to the first argument, which is y minus eta. And remember that we have to set eta equal to 0 when we calculate this derivative, so we can also write it as the derivative of psi with respect to y. And then remember that we have to evaluate psi. So when we take this derivative, we have to evaluate the overall quantity at yt. And then we have if you want to expand it further, you have eta squared divided by 2, and then you have the second derivative of psi with respect to y squared. So we keep all the terms up to second order, and then we still have minus the eta here. Let me tell you that when we multiply these terms together, we will keep only first order terms in epsilon. So here, when we consider this expression, remember that we have to take an integral over eta. So we have this exponential which contains eta squared multiplied by this, which is not a function of eta. So we have an integral of the kind integral from minus infinity to plus infinity e to the I m eta squared divided by 2 h bar xi d eta with a minus and also a factor of 1 over a if you want. The first term is this multiplied by psi of yt. This will be the first term of the expression when you multiply 1 by psi, and of course you also have to multiply by this and so on. So this is the first term. We will see that we will have to impose the fact that this quantity here is equal to 1. I will tell you why in a moment. Then we also have a second term here which contains eta, and the problem here is that this eta will appear inside an integral of this kind. We have this complex exponential, which is something that should be reminiscent of Gaussian integrals. So this is just a Gaussian integral with an imaginary unit inside, but that's a Gaussian integral, and it can be computed just like we do for real Gaussian integrals, and this is something that we can do thanks to complex calculus, so I will not get into the details in this case, but I have gone through the details on multiple occasions, for example in courses on complex calculus, but never mind, so this is not the point here. But when we have a factor of eta inside this integral, one can show that the overall integral is 0. So this term here will give us no contribution. And that's why we are keeping another term here, because this term with eta squared will give us a non-zero contribution. So this is the subsequent term to this one which gives us a non-negligible contribution. So we truncate all the subsequent terms, but we keep this one. So this is the next term that will become important. Not this one, because it gives a zero contribution, and this one by itself is not enough if you expand the expression. And you might get the idea if you expand the expansion, but I think that so far this is enough, so we can move on. And in particular, we can also expand the right hand side, which is this one. And in this case, when we think about epsilon, we want to keep only first order terms. So when we expand over epsilon, we keep only first order terms. And the expansion is very simple, because it is psi of yt plus epsilon derivative of psi with respect to t. So remember that also this term here should be evaluated at yt. Now you can see the reason why we have to impose the fact that this integral here gives us 1. And what does it mean that we impose it? It means that we have to choose a in such a way that the expression is equal to 1. And it can be done because this is just a Gaussian integral. It can be calculated. And by the way, there is no eta here, so this should not appear because it was just an example from before. And so eta does not appear, and we can choose a. I will give you the expression. If you just calculate the Gaussian integral, you can make sure that this is the case. A must be set equal to minus 2 pi I h bar epsilon divided by m to the power of 1/2. So this makes sure that this expression is equal to 1, and we have to make sure that this is the case because on the right we have a psi of yt, and on the left we must have the same quantity, psi of yt, and then we have another term which is proportional to epsilon as well, and we have to impose that also those terms are equal. So the term that multiplies epsilon on the right must be equal to the term or terms that multiply epsilon on the left. And so this can be done by noting that the integral from minus infinity to plus infinity of e to the I m eta squared divided by 2 h bar epsilon multiplied by eta. The eta, we know that this is 0. I said that before, so that this term here is negligible. And then we also have another term, a similar integral, but in this case we have eta squared, the eta. So we have something like this, and remember that this is also divided by minus a, which is just the square root of 2 pi I h bar epsilon divided by m, and this integral would multiply this factor of 1. So we do not multiply this term here by this factor as well, and the reason is quite simple, but it will become simple after we perform this calculation. If we calculate this integral, we can show that this is proportional to epsilon, and therefore if we multiply that by another epsilon, we would get epsilon squared, so that's negligible. And why is this proportional to epsilon? Well, this is a Gaussian integral, as I said, so it can be calculated, and one simple way to see that is if we call this expression here sigma squared, which is the variance of the Gaussian distribution. In this case we have an imaginary variance, so this is the standard deviation squared. And what we have here, for example, actually without the factor of 2, this part is just equal to minus 1 over sigma squared if you check. So it's quite easy to realize that. And therefore this is exactly a Gaussian integral which gives us sigma squared. But sigma squared is equal to I h bar epsilon divided by m. So if we put all these results together, what we get is minus I epsilon over h bar v of y multiplied by psi of yt. So this was this term multiplied by psi, and remember that the integral here will give us a factor of 1, because we have chosen a in such a way that it gives us 1, and we were forced to do that because of this first term multiplied by this, and therefore that will cancel this psi of yt on the right. So we are left with this, and we are left with the term proportional to the second derivative of psi with respect to y. So that gives us 1/2. So it's this factor here of 1/2, and then we have the integral containing this era squared, which gives us this. So we have I h bar epsilon divided by m second derivative of psi with respect to y squared, whereas on the right we are just left with this term here, epsilon d psi dt. Now if you multiply both sides of this expression by I h bar, you get exactly the Schrödinger equation, because you get minus h squared, so I will rewrite this term first, minus h squared divided by 2m second derivative with respect to y squared, and I will keep psi outside of brackets, psi of yt, and then here we have plus v of y, and this is equal to I h bar d psi dt. So I have simply divided everything by epsilon as well. Now you can see here that you have, so this is the momentum operator squared, p hat squared, and therefore what you have in here is just the Hamiltonian. So you have the Hamiltonian operator acting on the wave function is equal to I h bar d over dt psi, and that's just the Schrödinger equation. So that's that was the point of this video. This is something that is also written in the book that I mentioned earlier, written by Feynman and also Albert Hibbs, which can also be found online. So you don't necessarily need to purchase the book if you want to see what's inside and how Feynman describes the path integral. I think that this is actually a very interesting book, a well-written book, because Feynman is also a very good writer as well. And I think that's it for this video.